Hey class, welcome to our 5.5 video on conservation of energy. If you're wondering, where's the 5.4 video, Mr. Clark? You skipped one. 5.4 is a lab standard, so we don't actually have notes over it. It's actually proving what we're talking about today in 5.5, just in a lab setting. So we would have done that in class, so if you're a little confused where it went, that's where it just happened here in class for us. So let's talk about 5.5, conservation of energy. So before we talk about that, we have to talk about this idea of something called total mechanical energy. So in our class, we have a lot of objects moving constantly. And we've talked about two different types of energy. We've talked about gravitational potential energy, which we call U, and we've talked about kinetic energy, which we represent with K. Now, the total mechanical energy is both of those things combined. So if an object is up in the air and moving, we would add the potential and the kinetic together to get that total mechanical energy. We also talked about how friction pulls energy out of a system, and that is part of what's going on. So that work is a part of that total mechanical energy. So energy, or total mechanical energy, is just all the energy added up together inside of that system. And the reason we have to talk about that is because of conservation of energy. So conservation of energy states that the energy cannot be created or destroyed, only transferred between types. So no matter what happens, so if an object is moving and flying and then it falls towards the ground in free fall, well, that potential energy is going to convert into more and more kinetic energy because that energy has to go somewhere, okay? So what conservation of energy tells me is that whatever energy, total mechanical, I have at the start, I have at the end. And that's actually where we get this equation that's written here. So the total mechanical energy at the start is equal to the total mechanical energy at the end. And what we have to do is we can use this to solve for varying things. Normally we try to solve for maybe how fast an object's going at the end, or how high an object is at the end, or maybe how high it started because it's going so fast. And because of that, we have to get really good at identifying types of energy that are present. So let's go ahead and look at an example, and we're going to walk through a process here to figure out, okay, what energy is at the start, what energy is at the end, and then solving. So we're going to look at two examples as we go through this, but the first is going to walk us through it, and the second one's going to be a little bit more free form as we go through, okay? But we're going to leave that total mechanical energy, TME initial equals TME final, there at the top, okay? So let's look at a ball that we are simply going to drop off a cliff. So here is my cliff. Here's my ball. The ball is going to have a mass of 2 kilograms. It's going to be on top of a 20-meter tall cliff. And we're going to drop it. And our goal here, oops, sorry about that. Our goal is going to be to try and figure out, hey, when it gets to the bottom, what is its final velocity? So that's our goal here for this problem. 2 kilogram ball falls 20 meters. How fast is it going at the end? So I'm actually going to start with this right here. Total mechanical energy at the start equals total mechanical energy at the end. And whenever we work a TME problem, we have to ask ourselves two questions. So two Qs. Question 1, and we ask ourselves at the start and at the end, is the object above h equals 0? Is it above the ground? If we answer yes, that means UG is present, okay? So if it's above h equals 0, we have gravitational potential energy. The second question I ask is the object moving? If we say yes, that means kinetic energy is present. Okay? So I ask myself these two questions, and I ask mine at the beginning, and I ask it at the end. So we're going to come back over to our ball on the cliff here, and we're going to ask. So at the start, when I drop this 2 kilogram ball off the cliff, is it moving? Yes. Yes, it is moving. So that means no. Sorry, I'm getting mixed up here. No, it is not moving. I asked the questions out of order. So no, it is not moving, so I don't have kinetic energy. But is it above h equals 0? H equals 0 is the ground, and it is. So at the start, I'm going to have potential energy at the beginning. Okay, at the end, am I above h equals 0? Well, no, I hit the ground, so I don't have any gravitational potential energy. But I am moving. Is the object moving? Yes. So I have kinetic energy at the end. And if you can get this far, you are 80% of the way there. This is the concept we're trying to get. From this point, it's just kind of math. So I can plug in my equations. So I can use my mgh initial for that potential energy. Kinetic energy is 1/2 mv squared, or v final squared. And now I just got to figure out the math side here. I got to plug in values and do some algebra. The hard part here is sometimes rearranging those variables, but there is something that's really nice. If you notice, it shares m in every single thing, which tells me that masses cancel. So I'm left with gh equal to 1/2 vf squared. I'm going to multiply both sides by 2. So I'm going to get 2gh naught equals to vf squared. And then I take the square root, which gets me that the final velocity is equal to the square root of 2 times g times that initial height. And now I can simply plug in values, right? I can plug in square root of 2 times 10 is g times my height of 20, which gets me the square root of 400, which is going to be 20. So I end up at 20 meters per second. So again, the question is, what types of energy are at the start? What types of energy are at the end of our problem? Okay? So we're going to look at one more example, and we're going to add a little bit more into this now. Okay? So second one is going to be a fan favorite of energy problem makers. We're going to look at a roller coaster. Okay? So at the top of this first hill, ooh, great roller coaster, okay? So this first hill, we're going to mark it at 60 meters tall. And the second hill, we're going to mark at 30 meters tall. And at the top, I'm going to be moving with an initial velocity of 5 meters per second. So we're just coming over that first hill. And what I want to know, similar to last time, what's the final velocity of this car? So before you might try and say, well, we could use kinematics or we could use energy, but the problem is this is not consistent. It's not going to be accelerating at the same rate the whole time. So it's going to kind of be slower at the top, and then it's going to be slow up here, and then it's going to speed up really fast, and it'll start slowing down as it goes up the hill. And so because of that, it's inconsistent. But I can use energy, because whatever energy is in the system has to stay inside of that system. We're assuming no friction, right? So I would start off like I did my last one. Total mechanical energy at the beginning is equal to total mechanical energy at the end. And I ask myself at the beginning, am I above h equals 0? Yes. So I've got potential energy at the start. Is it moving at the start? Yes. So I've got kinetic energy at the start. At the end, am I above h equals 0? Yes. So I have potential. And am I moving? Yes. So I have kinetic at the end. And again, if you can get to this step, it's just algebra now. It's just plugging in your equation and then plugging in values, okay? So mgh naught plus 1/2 mv naught squared equals mgh final plus 1/2 mv final squared. Oh, that's a lot. It's a lot of variables. But again, the same thing happens here. Look, m. So m's all cancel, as long as every single one has it in there. So I've got gh naught plus 1/2 v naught squared equals ghf plus 1/2 vf squared. Now for some of us, we may want to plug in numbers first and then solve. So I'm actually going to solve that one this way as opposed to doing the algebra first. So I'm going to plug in, we're going to have, I'm going to move this over here for us. So we have 10 times 60 plus 1/2 times 5 squared is equal to 10 times 30 plus 1/2 vf squared. I'm going to solve all these out, so I'm going to get 600 plus 12.5 is equal to 300 plus 1/2 vf squared. I have to subtract 300 from both sides. So that's going to end up giving me 312.5 is equal to 1/2 VF squared. Multiply both sides by 2, because that cancels out my 1/2. So I end up with 625 equals VF squared. Take the square root, and I end up with the square root of 625, which gives me 25 meters per second. There we go. So you can see how the energy interacts. Again, whatever happens at the start has to happen at the end. Now, you might have to solve for an initial height, or you might have to solve for an initial velocity, or a final height, or all sorts of things. But that combination can be any. It doesn't have to be both. It could be you have one type of energy and then two types of energy. It just depends. You have to read the problem here. So 5.5 is going to give you plenty of practice with this skill, talking about total mechanical energy at the start and then total mechanical energy at the end. As always, if you have questions, come reach out to me in class. Send me an email, and guys, as always, don't forget to be awesome.